Hello and welcome to the fourth practical of the subject Applied Electronics. Myself Sanjit Kumar Singh, lecturer at Electronics and Telecommunication Department at Praveen Patil College of Diploma Engineering and Technology. So this is a practical of single stage common source FET amplifier. So we are implementing this circuit on a breadboard, and with respect to frequency of the input signal, we are noting down the output voltage at different frequency. So prior to performing the practical, what are the learning outcomes or the practical skills competencies required that will be developed after going through this presentation or after seeing this practical is to use discrete electronic devices. Secondly, the course outcome is to use transistor as low power amplifier, and practical outcome is to build or test the performance of the single stage common source FET amplifier. So since it is common source FET amplifier, we are connecting a resistor in the source path and is grounded. The source is grounded. That's why it is called common source, and the grounded source is common between the input and the output. The VCC is applied here is 12 volt, and the value of the components taken, the transistor FET transistor we have taken BFW 10 for our practical, and resistor as we see R1 and R2 are the potential divider resistors of 300 kilo ohm and 200 kilo ohm respectively. The Cin is of 50 microfarad input capacitor, and output capacitor is of 10 microfarad, whereas the common source bypass capacitor is of 100 microfarad. The RD value we have taken as 2 kilo ohm and the source resistance of 3 kilo ohm. So in order to take the readings, we are implementing this circuit on a breadboard. So here is the transistor, this is the transistor BFW 10, that is the FET, and this is the input capacitor of 50 microfarad, R1 of 300 kilo ohm, R2 200 kilo ohm, RD is the RD of 2 kilo ohm, and RS of 3 kilo ohm. Here we have the output capacitor, output coupling capacitor of 10 microfarad, and here 100 microfarad capacitor as the bypass capacitor. So in order to take the reading, we are feeding the input to the gate with respect to source from a function generator. Now right now it is at 1 kilohertz, and the first channel shows the input, whereas second channel shows the output. Okay, so for this input and the VCC 12 volt, the output provided is observed and is taken from the coupling capacitor with respect to ground and is observed on the second channel, and the output we are seeing is 1 to 2.8 into 50 millivolt. That means it is 2.8 into 50 millivolt will be 140 millivolt output we are getting at this input. The input is of 50 millivolt at 1 kilohertz. Now similarly we are noting down the observation table readings in the observation table. Here we have the 1 kilohertz. We have taken the reading 160 millivolt as the output. Then so this is at 100 hertz output we are getting. So this is again 2.8 into 100 millivolt. The volts now is at 100 millivolt. 0.1 is 100 millivolt. So similarly for the 100 hertz we have noted down 580 millivolt output. Then this is the output for 10 hertz. 10 hertz frequency, the first channel is the input of 50 millivolt and the second channel is output. So here we can see the output is changing from here we can see the output swing is between 4 divisions and 1 division is of 100 millivolts. So near about 300-400 millivolt output we are getting even at 10 hertz input frequency. So it provides amplification at even low frequency input signal. So we are noting down the value we have taken earlier. For 10 we have the 420 millivolt output. So in this way we are going on changing the frequency and noting down the readings of the output provided by the FET amplifier. This is the at 100 hertz. Next, this is at 1 kilohertz. Per division it is at right now it is at 100 millivolt. So it is near about 140 millivolt at 1 kilohertz. This is at near about 10 kilohertz. Output is somewhat reduced compared to previous output. So this is the output at 108, that is near about 100 kilohertz. Next, this is at 1 megahertz. At 1 megahertz we have almost 100 millivolt output. One division is of 100 millivolt. The second channel is the output, first channel is the input. First channel is at 50 millivolt, whereas second channel is at 100 millivolt. So even at 1 megahertz we have the amplification. So in this way we are taking the readings. So here we have the readings for the different frequencies and calculated the gain at different frequencies. This gain is converted into dB by using the formula 20 log V out upon V in. So we are getting this gain in dB, and graph will be plotted between frequency versus power gain or voltage gain here in dB. So for sample calculation, here we have the sample calculation, and for graph we have plotted. This is the graph we have plotted. So here the maximum output is obtained, maximum gain is obtained at near about 100 Hz for our practical circuit, and the 3 dB frequencies, the upper frequency we are getting 210 Hz. This is starting with the 10 Hz here, 100 Hz, 1 kilohertz, and so on. So and FL, lower frequency, cutoff frequency, is at near about 9 Hz. So 3 dB down we are plotting these cutoff frequencies, the where this dash line cuts the main curve. Those are the cutoff frequencies, and the bandwidth calculated as upper cutoff frequency minus lower cutoff frequency, that is 210 minus 9 is near about 200 Hz. So we will get 200 Hz as the bandwidth practically, or even in kilohertz we can get. So here we have written the result, 200 Hz as the bandwidth, and 21.3 dB as the maximum gain in this reading, obtained at 100 Hz, 21.29 we are getting as the maximum gains. So that's it. Thank you.